Oke. Ya, Assalamualaikum warahmatullahi wabarakatuh. Selamat siang Bapak Ibu sekalian.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat datang di Colloquium kelompok keahlian astronomi ITB. Kali ini Colloquium akan menghadirkan pembicara dari Jepang, maka bahasa akan dialihkan ke bahasa Inggris. Okay, thanks everyone. Good afternoon. For joining us today in the Colloquium of Astronomy Research Group, ITB. And today we will have invited speakers from Kindai University, Professor Taro Inoue. And today he will talk about probing dark matter with a strong gravitational lensing. So before we start the colloquium, I will tell you about the short introduction about Professor Inoue. So Professor Inoue has graduated from International Christian University for his bachelor, and he continued his master's and also a PhD from Kyoto University. And now he is a professor in Kindai University at the Department of Physics. And today, Inoue-san will introduce the physics of gravitational lensing, freestreaming of dark matter particles, the small-scale problems and methods for measuring dark matter fluctuations on small scales. Then he also will review his group's recent works and discuss about the future prospects. So for discussion, maybe you can participate for a discussion session at the end, by the end of his presentation. So maybe let's start to Inoue-san presentation. Please, Inoue-san.
Thank you very much for a very good introduction. Can you hear me okay?
Yes, we can hear you.
Okay, so hello everyone. I'm Kaiki Inoue. Nice to meet you. And first of all, I'd like to thank Anton-san and Premana-san for giving me an opportunity for a talk. So today I'm going to talk about strong gravitational lensing for probing dark matter. And the subject is very broad. Actually, it is an interdisciplinary field which concerns about particle physics and galaxy formation and cosmology. So I think it is very difficult to review all of the area. So if you have a difficulty, please feel free to make some questions every time. Okay, so this is the outline of my talk. First of all, I start with a brief introduction of dark matter, and then the so-called missing satellite problems. This problem has been the main motivation for these 10 years for observation. And then a very brief introduction for the gravitational lensing. And after that, I will talk about my recent research results for 8 years, from 2012 to 2017, about 6 to 7 years result. And also the recent observational results. Okay, so these are the references. Okay. The motivation of my research is to find what is the dark matter. From the point of view of cosmologists, we divide dark matter models into basically three categories based on its sort of coldness of particles. One is the so-called hot dark matter, which has a large velocity dispersion as a decoupling time. Here we consider only dark matter, which consists of elementary particles. All of these elementary particles exist in the very early epochs in the universe. And because the temperature of the universe was very high, so the particles interacted each other. And in the very early phase, all of the particles interact each other. So because of such interaction, we can consider the particles as a single fluid. But eventually, the temperature of the universe become decreased and become cooler. And then some particles, here we consider dark matter particles, started to decouple with the other particles. In that period, the dark matter particles had some velocities. So if the velocity of the dark matter particles is almost equal to the light velocity, it is called hot dark matter. And if the velocity is very small at the time of the decoupling, it is called so-called cold dark matter. And in between the hot dark matter and the cold dark matter, there's another category, so-called warm dark matter. So please remember that basically from the point of view of cosmologists, there are three types of dark matter candidates. So the problem is how we can make a distinction between these models observationally. So this is a picture of diagram of the particles, which has a velocity in the very early phase of the universe, at which the radiation energy dominates the energy density. And if the dark matter particles decouple from other particles, it randomly goes free streams until the other particles has the same velocity due to the Hubble expansion. So the free streaming stops when the velocity of the particles is equal to the other particles Hubble flow. So until that time, the particles freely stream. So that means the fluctuations is erased. So that is so-called suppression due to free streaming. That is a very important physical mechanism. So in the early era, fluid of particles make some structure due to the primordial fluctuation seeded by probably the inflaton, and then it will grow. Because of the fluctuation, amplitude of fluctuations for smaller scales is larger than large scale fluctuations. Small scale fluctuations start to grow first, and then it will the small fluctuations make some small structure, and then these small structures merge together to make much larger objects, like this image. And then small structures merge together and makes a large structure. That is a structure for hierarchical structure formation. But if the dark matter has a large velocity dispersion at the decoupling time, it will erase the structure. So-called freestreaming scale is a very important scale here, so L3, which is proportional to the m to the minus 4/3. That means for a large mass, here m is the mass of the particle, and if the mass is very small, that means the free-streaming scale is very large. So it may be inconsistent with observation. So the typical scale is if the particle mass is about 1 kilo electron volt, that means the free-streaming scale is 1 megaparsec. So here, 1 parsec means about 3 light years. So 1 parsec is very large length, and megaparsec is 10 to the 6 times. So the free-streaming scale is actually very large, even the mass is 1 kilo electron volt. So if we consider neutrinos like maybe smaller than electron volt, so that streaming scale is quite large. So here is the simulated results by Schneider et al. A bit old. Anyway, the left hand 3 figures show this structural formation in the cold dark matter model, and the right hand 2 rows correspond to the simulation results for warm dark matter with 1.0 kilo electron kb mass and 0.25 kb mass. So you can see that the here Z is a redshift in the universe of the structure, and this is Z equals 4.4 means where the size of the universe was about fifth of the present time's size. And then the structures grows like this in the early phase, and Z equals 1, and here is the present time. You can see that the very small scale structures here. But if you see the right-hand side figures here, you can see that the fluctuations are somewhat smooth or some sort of coarse grained. You cannot see any small structure here. So that is due to that's because of the free streaming by the warm dark matter in the radiation dominant areas. So basically these figures show the shows how we can make a distinction between the cold dark matter model and warm or hot dark matter models. That is the some sort of clampness for the small scale fluctuations. Okay, so here the velocity dispersion, the decoupling time is quite important because we observe many clusters of galaxy, which is large, whose scale is larger than say 10 megaparsec. So that means hot dark matter is now ruled out, almost ruled out. But we can consider the dark matter called warm dark matter, which has a smaller, shorter free streaming scale. Of course, CDM looks now very good for the scales larger than 1 megaparsec. But the problem is that it may be inconsistent to dwarf galaxy scales that correspond to the about 10 kilo to 1 megaparsec scales. Okay, so the problem arises from so-called missing satellite problem. What is that? So here you can see that in the left-hand side figure, this is a real observed cluster of galaxies. So these represent yellow, some spots correspond to individual galaxies. So you can see the cluster, a cluster of galaxies here. And this right-hand side shows the distribution of dark matter particles in the numerical in a numerical simulation. So you can see that both simulations shows some sort of clumpiness. Actually, the data is almost consistent on cluster scales. But on the galaxy scale, the correspondence does not no longer hold. So you can, this is the figure of observed elliptical galaxy, so-called M87, observed by Hubble Space Telescopes. And the right-hand side, this is a simulation on the cluster scale. But for galaxy scales, almost the same. This is the recent numerical simulation for the early type galaxy, and the size, the radius size is about 600 kilopascal scale. So that this corresponds to the very massive elliptical galaxy scale. So you can see that still you observe, you can observe many spots which correspond to the subclumps. So we call these the so-called sub-halos in the dark matter apparent halo. But in the observation, you cannot see so many, at least bright dwarf galaxies. You can see here and here very only 2 or 3 dwarf galaxies, but the number is quite small compared with the prediction from new and n-body simulation. So this is the figure of the distribution of satellite galaxies in the Milky Way near Milky Way galaxy. Observation showed that the number of satellite or dwarf galaxies just 40. But on the other hand, n-body simulation results show that the number is about more than 500. So here is the cumulative number of halos in terms of so-called circular velocity. Circular velocity is a good indicator for representing the mass of halos. So here, this is a large halo. Halo means a clump of dark matter particles, and there's a galaxy here. This is only for Milky Way type galaxy, but anyway. So dark matter particles are moving around in a halo, and the circular velocity is velocity of a dark matter particle which has a circular orbit. So if the circular velocity is large, that means a large halo, and if the circular velocity is small, that means a smaller halo. So basically here, 0.1, for instance, corresponds to the 10% of circular velocity compared with the parent halo. So the dwarf spheroids and Fornax and Sagittarius, here the satellite galaxy has circular velocity about 20 or 10 or 5% compared to the parent Milky Way galaxy halo. So the number is still 4 now. This is a certain older data, but now it is about 40 or maybe 50 or something like that. But still, we have one order difference between the theory and observation. So this is the so-called missing satellite problem. Where is the satellites? Where they go? Where did they go? So that is a problem. So simulated dwarf galaxy sized dark sub-halos are larger than observed dwarf galaxy. So basically, I think that there are 2 ways to solve these problems. One is baryonic fields, also large scatter, but I think now it's almost dead. So I think the first choice is baryonic physics. That means that there may be very large number of very faint dwarf galaxies that we have not observed yet. maybe more than 400, satellite galaxy remains to be observed. Or it may be due to the dark matter physics. So if we consider the warm dark matter, for instance, model, because the streaming can erase the small scale fluctuation. So the problem is whether we can observe very faint dwarf galaxies, or in other words, are there any matter fluctuations on scales less than 100 kilopascal scales? So if we have matter fluctuations on that scale, that means that there are many dark halos, which is consistent with the cold dark matter. But if there are no such dark halos, if there's no dark halos, then of course there are no satellite or dwarf-sized galaxies. So it is very important now to make constraints observationally for the number of faint dwarf galaxies and also the dark halos with smaller mass. So how we can observe such fluctuations observationally? So there are actually many methods. For instance, if you want to observe faint ones, you may use very large telescopes. That may be okay. But it is very difficult to find, for instance, to completely dark subhalos because there's no objects which can emit radiation. So in that case, we have to use either kinematic information or distortion of photon path due to gravity. So now I'd like to talk about the gravitational lensing, actually, which can make some constraints on the distribution of dark halos. So I make a brief review for the gravitational lensing. So gravitational lensing is a phenomenon in which light path is distorted by intervening mass. So here, this is sorry. So here, this is a source, right? Source, and this is the lens, which corresponds to the dark matter halo, a clump of dark matter particles. And if an observer and lens on the same line, and if the source is close to the line, then the light path is bended by the gravity of this object. This is the result from the general relativity. And the important physical property is the so-called deviation angle here, denoted by alpha hat. So alpha hat is how it measures how it is the light path is bended. And the alpha hat is represented by the gradient of the gravitational potential projected onto this plane, so-called lens plane. So if we can measure this bending angle, but we can measure the gravitational acceleration on this point. So that is the essence of gravitational lensing. And also, we not only the bending angle, it is corresponds to the so-called astrometric shifts of each image, but also we can measure the second derivative information. That means the so-called they are so-called convergence. convergence can be obtained by taking the trace of the Hesse matrix for the projected gravitational potential psi divided by 2. And that is correspond to the difference between the bending angle for the infinitesimally close right path. So here the delta, so delta actually alpha hat corresponding to the if the trace part is the so-called convergence. And convergence means that if the convergence is positive, that means the source is magnified without distortion. And if it is convergence is negative, kappa is negative, it corresponds to the shrinking of the source. So the demagnification. And also we have to consider so-called the shear. So that corresponds to the traceless tensor for of the Hesse matrix for the gravitational potential, projected potential psi. And shear measures the distortion, but without any magnification or demagnification. So in this case, the source is a star, and if there's a shear, then the star is squashed in some direction. So this second derivative information is also important because this image distortion will make a difference in the observed flux. Because we can measure flux, we can measure shear and convergence. And if we can measure the shift of each lensed image, we can measure the gravitational acceleration alpha. So here, convergence kappa and shear gamma and alpha shift are the very important physical properties. And this is the Einstein ring here. So if the source is on the line which connect to the observer and the lens, the center of lens, and if the lens is completely circularly have a circular symmetry, then the point will make some Einstein ring. So let's make some experiments by myself. I actually have some real lens, but of course it is not a gravitational lens, but it somehow mimics the gravitational lensing effect. So I made, actually my students made this, lens, but actually it is not a lens. This is just just a cone-shaped lens. So if you see through this gravitational lensing lens, you can see the effect. So this is, can you see this? I hope you can see this now. Okay, so this is the source, and I hope you can see. So this is the gravitational lens. So if you see that, you can see that it's very difficult one. So there are two images and make Einstein ring. And the two. Okay. Were you able to see this? I hope so. I don't know. So this is the Einstein ring, and so I want to explain about some jargons, so-called the caustics and the critical curve. Caustics is a point for which the corresponding light ray at the so-called lens plane, then if the magnification becomes infinite, it is called caustic. So in this case, the very center, in the case of circular symmetric lens, the center is so-called caustic point, which will make an Einstein ring. And also there's a so-called cut here, which correspond to the center. In this case, we are considering the matter distribution in which the density becomes infinite at this center. So here, the cut blue part is mapped to the center, and the center here, so-called source plane, the source plane is mapped to critical curve, which corresponds to Einstein ring. So this is a case for a circularly symmetric lens with a singularity at the center. And if the circular symmetry is broken, for instance, in the case of elliptical symmetry case, the caustics now has a diamond shape like this, not point, and then this at the point in this caustics correspond to the critical curve here. And so then it will make some differences between the circular symmetry case and elliptical cases. So this is the case of the figure that shows the image, lensed image in a circular lens. So this is the source plane, and this is number 2, and this is lensed image at the source plane, sorry, lens plane. So if we put 2, we will observe two images, but with a different parity. So you can see that the parity of this image is the same, but inside the so-called cut region, you can see that direction in the x here, but horizontal axis corresponds to the x-axis, and for x-axis it is flipped, so it has a negative parity. So this parity is quite very important because it is related to the perturbative effect due to sub-clamps or sub-halos in the line of sight. And this is the parity in the elliptical lens. So similar to the case in the circular symmetric lens, we put actually about 10 points shaped number 2, like this. But we have some, so-called caustic diamond shaped caustic, and this is the lensed image. And you can see that there are 4 images. Actually, there are maybe 5, but in this case, the center point is singular. So it is cut, and the 5th image cannot be observed. And we can see 4 images with 2 positive parities and 2 negative parities. So this property is quite important. Because of this, actually, we can make a distinction whether this is due to the halos or due to some voids. We can make a distinction by using this parity information and flux and or shifts. Okay, so if we put, suppose we put another lens in addition to the primary lens due to maybe sub-halos or halos in the line of sight or maybe voids. So it will cause another lensing effect. So suppose that we put another lens like this on the parity on the lensed image with positive parity. Then it will be magnified because the source is expanded in all that direction. But in the case of a negative parity case, this is different. In this case, the source is expanded in one direction, but in another direction, it will be squashed. So that means the image can be demagnified. In some cases, if the expansion effect is larger, then it will be magnified. So it depends on the value of kappa and gamma. But anyway, the property is different. Changing property is different. So in the case of plus parity, it always magnified, and the plus minus parity case, demagnified or magnified. So let's consider the photon path for each case. Suppose first we consider plus parity case, positive parity case. This is a source plane, and this is a lens plane, and here there's an observer here. And suppose the source is lensed by the primary lens. In this case, we have some sort of plus positive convergence. So this source, this is a point, and the light starts from here and departs here, and then deflected by the primary lens. So in this case, these lines is bended by like this, and outer part goes pass through like this. And then we consider another lens, put another lens on this lens plane, and see what will happen. So because in this case, lens acts as some sort of concave lens, then it will make another another plus deviation. So that means if there's no here red lens, it will deviated by, distorted by, bended by like the yellow line. But if we put a small lens here, the light path will be changed to this line. So that means the image shift is outward. The direction of the image shift is outward. But in the case of negative parity case, it is no longer true. Suppose a negative parity case. In this case, source plane, the photon departs from this other direction. So it will goes like this. So if we consider innerward light path, it will bend like this. So in this case, because the image is flipped, the change is somewhat different compared with the plus parity case. Then we suppose put lens here. So what will happen? So in this case, if there's no lens here, sub-lens here, the light path, if we consider light path as a red line, it will change as this. Because, you know, the light bending angle is a function of the position. So the bending angle is the same as the green line. So it will bend like this. So if we put another lens here, it will be again bended. So it will move back to the observer. So in this case, shift changes inward. So it is opposite compared to the positive parity case. So that means the image shift has a dependency on the parity. This is a very important effect. Okay, so let's go back to the observation. So assume a smooth potential which describes the gravitational potential of a smooth elliptical galaxy. And there are many observations, and it has been known that the positions are well fit using a smooth potential. However, some systems show that the flux ratios of lensed image are not well fit, about 10% error. So that what has been the problem. So people in the literature, many researchers consider that this may be evidence for subhalos in the lensing galaxy. And our group actually observed lensed quasars. Quasars is a very bright object, and actually there's a supermassive black holes, and the surrounding gas is moving very with a fast velocity, so it will emit very bright light. So we can observe very distant universe using this so-called quasar. And the quasar galaxy lens is a lens in which the source is quasar and the lens is galaxy. Here we consider elliptical galaxy, so the gravitational potential due to the lensing galaxy halo is relatively smooth. And we have conducted the observation in the mid-infrared band because in the optical data, this is optical data by Hubble Space Telescope, but in this case, there's a cavity that is the micro-lensing effect due to stars. Because in this case, a galaxy has stars, right? A galaxy consists of many stars. So stars can also deviate the fluxes of quasars because the source size is very small, actually. But we want to observe the so-called mid-lensing due to subhalos or some other halos in the line of sight. So we need a more larger source compared to the optical or near-infrared quasar. So we have conducted observation with mid-infrared band. So it is free from dust extinction and micro-lensing due to stars. So this is the these figures show the observational result for 6 lensed quasars, and we have measured the flux ratios, and we have found that there are 3 anomalies. So these 3 systems show some unknown origin of gravitational perturbation, perhaps due to some structures. And this is the near-infrared image, observed by Hubble Space Telescope. And here, this image consists of 4 spots, A1, A2, B, C. And the flux ratio is about the brightest 2 spots, about 0.4. It's divided by A1. But actually, if we observe with mid-infrared band, actually the ratio is 0.9. So if this is 1, that means there's no anomaly. But actually, it is deviated by 10%. 10% means actually very large. So we have observed or we have confirmed that there is actually anomaly around these objects. So this is a simple model of that corresponds to the MGJ0414 plus 0534. So you can see that there are 4 image, but with 2 negative parities and 2 positive parities, and these 2 correspond to the bright spots here. So if we put some clamps near these images, it will it will perturb the fluxes for these images. That is the point. So what is the origin of the flux ratio anomalies? There are many possible origins. First of all, subhalos in the primary lens. That has been studied many years. But here, I'd like to make emphasis on the importance of line-of-sight structures. And also, a complex primary lens can be possible this. But I concentrate on the second possibility. So we consider a lens system like this. We observe here using telescopes, and the source is deflected. The light source is deflected by lensing galaxy here, but also we have to consider subhalos in the lensing galaxies and also line of sight structure like this. So which structures are more important? That is the question. So previous studies on line of sight structures only rely on halos. So galaxy people who studied galaxy consider small scale structures consist of halos. That is true for understanding galaxies. But actually, line of sight structure is related with the effect in cosmology, not galaxy formation. So I wonder at that time, when I was at Oxford, I thought that whether this idea was this, I thought that some problems may be relevant because they are only considering halos, but not considering fluctuations. So I thought that the peak densities may not be good tracers. Let's consider the some system. So you can see that the source is lensed, and you can see 4 lensed image. And then you input some halos, but it is spherical symmetric. So it looks like, as the first approximation, it may look good. But actually, if you consider all types of fluctuations, you can see that it is no longer true. So we, our team, collaborators, run n-body simulation. So more realistic data shows like this. So this is convergence obtained by an n-body simulation with very high resolution. You can see that objects are clustered, and also you can see a negative dense convergence region. So it is very, very complex. So suppose there a cut line like this. If you measure the density fluctuation on this line, it will like this. So here, red color shows a very large density, very dense region, and blue color is void regions and cluster, something like this. So it is very, very complex. But the chance of having a halo very near the very close to the lensed image is very actually small. For instance, this stars reside in a void, not here. So that means we have to consider the four fluctuations at the same time. So instead of considering halos, I have considered fluctuations in terms of, in other words, matter perturbations or potential perturbation. And I divided such fluctuations by the wavelength. So if the wavelength is equal to the size of the Einstein ring, I name here k length. K is the wave number. And if the wavelength is longer, that corresponds to large scale fluctuations and large mass halos. And just for short scales, which correspond to the smaller halos or smaller voids. So here I decomposed these contributions by the observational properties. So suppose perturbation by these fluctuations. If fluctuations had a large, long wavelength, that will make a large difference because the mass scale is large. But if the the length of the wavelength is short, which corresponds to smaller mass, so that means the effect is very small. So by this, I decomposed the contribution because we can, fit the lensed image positions by model with the smooth potential. We can fit, but there remain residuals. That is the delta theta. We cannot explain the very small scale residual fit between the separation. So each lens image distorted by very small size. So that determines the possible contribution scales. So here delta theta cut, sorry for this, delta theta cut determine the k cut, which determines the possible fluctuation scales that can affect flux ratios. So this is the figure that shows the astrometric shift perturbation in terms of the wavelength or wave number. So here, for instance, red dashed curves correspond to the image separation about image separation with 1.5 arcsec. And the blue dashed lines correspond to lensed image, a pair of lensed image with separation of 0.5 arcsec. And if the wavelength is very larger, that means the smaller wave number that corresponds to the supercluster scale or cluster scale. And if the size is about 1 megapascal, it corresponds to the galaxy scale. But the image shift, typically the size is about 3 milliarcsec, very, very small fluctuations. So if we write, if we constrain from the observation of the separation perturbation, 3 arcsec, 3 milliarcsec, that corresponds to the here about 300 H per megaparsec scale. That is the mini halo or dwarf size galaxy halo scale. So in this method, I decompose from the observation the possible contribution of perturbers. So I'm not using any information for the halos, but only using the fluctuation. And then I used another new statistic called eta, which, sorry, this is eta, sorry, magnification perturbation. Eta is basically the correspond to magnification contrast, how image magnification is distorted by the presence of a subhalo or line of sight structure. So here we consider AC, image AC with positive parity, and B, negative parity images, and then eta can be defined by this. Basically, we fit the image position with smooth potential, and then we obtain the non-perturbed zero approximation of fluxes A0, B0, C0, and then using these values, we can measure the eta. So eta is corresponding to the variance in the magnification perturbation plus correlation between the different images. So in this case, eta squared is equal to the 1/4 of the delta A minus delta B squared. So that means there's a correlation between the delta A to delta B is also taken into account. So that means the single halos can at the same time make perturbations for the A image and B image with different parities. So this is the new statistics I have considered. And using these statistics, I applied to the 11 quadruple lenses, and I measured, I used observed flux ratios to calculate the convergence perturbation for these quadruples. So these convergence perturbations correspond to the either subhalos or line of sight structure. And I made the assumption that the convergence perturbation is equal to the shear because for homogeneous and isotropic fluctuations, it has been known that the convergence perturbation is equal to the shear perturbation. Although in each lens image it is different, but altogether for 11 cores with 4 images, the difference can be neglected. So you can see that this, these red figures, these red anyway, can you see this? Okay, this figure shows the observed result. The horizontal axis corresponds to the source redshift, and you can see the very okay, so dispersed data, but somehow you can see some trend that is for the larger source redshift, the convergence perturbation becomes larger. And I also calculated theoretical values for line of sight structures and subhalos. You can see that in the case of line of sight structures, the convergence perturbations increase as a function of source reds. This is a natural result because if the source redshift is larger, that means we can measure a long length. That means that there are many structures in the line of sight. But subhalos do not show such things because here subhalos is rated with lensing redshift, not the source redshift. So there's no such correlation. So I combine the result for line of sight and subhalos. Then I compared the result, and they looked very consistent. So that means the line of sight effect is quite important compared with subhalos. And this plot, okay. So anyway, this is a plot that shows the contribution difference this figure shows the ratio between the contribution from sub-halos and the total contribution. So here you can see that for the source redshift 0.6, sub-halos contribute only 40%. And for the source redshift, about 3.6, very far away, the total relative contribution from sub-halos are just 20%. So that means the sub-halos are subdominant. In other words, line of sight structures are dominant. And this is a simulated power spectrum for warm CDM and warm dark matter models. And by using these simulations, we have obtained that from the observation of lensed quasars with using flux ratios, we obtained a constraint for the warm dark matter model that the mass is larger than 1.3 Kep. And the free streaming scale is larger than 230 kiloparsec scale. Also, we have considered the so-called mixed dark matter model, in which dark matter consists of warm dark matter and the CDM. And we have obtained that this region is prohibited. Here, R warm corresponds to the ratio of warm dark matter component compared to the total dark matter. So 1.0 means 100% warm dark matter, and for instance, 0.4 means 40% warm dark matter and 60% cold dark matter. So you can see that if warm dark matter 100% the cases, about 1 kilo kb is the constraint. But if the ratio of warm dark matter, I mean, it is less than 40%, then it is allowed. So that means still very small mass warm dark matter is actually not constrained at all if we have some cold dark matter component. That is our result. Okay, so and also line of sight lensing. In order to understand the line of sight lensing, we have to consider not only halo but also the voice. But we can only observe the integrated effect. So we can only observe some sort of trough structures. Trough correspond to the very thin underdense region, whose size is 1 kilopascal, typically 1 to 10 kilopascal scales in the direction perpendicular to the line of sight. And in the line of sight direction, the size is 1.1 to 10 megapascal scale. So it is very, very thin object, but with underdense range region. But we can directly observe such trough using gravitational lensing. So as you can see, this convergence map you saw in the previous slide. These bright blue regions correspond to the troughs, and the red regions correspond to halos. So probably the actual universe like this. So that means the line of structure is very complicated, but including the positive density halos and negative density troughs. And also, I want to tell you about our recent observation result. First of all, we used the so-called lensed submillimeter galaxy, which is very bright at submillimeter length, with ALMA. ALMA is a telescope, radio telescope, or the submillimeter band, the largest telescope in the world. And I obtained a very interesting feature that is actually such a negative density perturbation might be observed. So that may suggest the existence of line of sight structures. So here is the lens image, observed lens image SDP81, and which consists of 4 lens images and 2 doubles. And this is the modeled for quadruples regions A, B, C, D. And I have found that the perturbed spot in B, which corresponds to plus positive parity. Actually, it should be always magnified. But actually, I have found that it was shrinked. In this case, B should be magnified if this is perturbed by a halo. But actually, it has been squashed, demagnified. So that may imply that actually there's an under-dense region, trough in this region. So maybe it's better to check in near future whether this structure is true or not. Maybe a trough at B and a halo at C. Okay, and next MDJ, another lensed quasars. I obtained a very interesting emission in the submillimeter band. We observed some very faint submillimeter emission that may correspond to halos. I don't know whether this is related to subhalo or line of sight halo, but it looks like there's a halo, small mass halo in this region. So maybe it is a dusty dark dwarf galaxy. Dust mass is 10 to the 6 to 7 solar mass, but it may explain the 10% decrease in the lensed image as well as the dust extinction observed in optical or near infrared fluxes. Of course, we have to verify in the near future about this model, but it looks like all observations are consistent. Okay, let me summarize. Gravitational lensing can be used for detecting dark halos and troughs at the cosmological scales. And the line of sight structures dominate over subhalos for changing flux ratios of lensed quasar image. And the CDM model seems to be consistent with observations on scale of 1 kiloparsec scale, suggesting that numerically optically faint dwarf galaxies reside in the universe. So far, there's no inconsistency between CDM and observation on this scale. But if we go to the smaller scales, we don't know yet. So I think it is very good to continue this type of research. Thank you very much for listening.
Okay, thanks for very good explanation, Inoue-san. So now I would like to invite the audience if there is someone who wants to give a questions. Okay. I don't know if Prodi Sarjana who is that. Maybe you can open your mic and you can tell the question directly, please.
Okay, it's me, Anton. So, thank you very much, Professor, for the nice talk. I would like to ask, what is the chance that the missing satellites is caused by our incomplete understanding of how galaxies get built? So instead of trying to explain or looking for explanation for the missing satellite, maybe is it what is the chance that it's because of our incomplete understanding on how galaxies get built? Okay.
That is a very difficult question for me to answer. because it is related to the galaxy physics. So, but I think, in my opinion, the missing satellite problem is probably observational some sort of bias, because astronomers use a telescope. So naturally, it is very difficult to find any very faint, very diffuse galaxies. But in these years, the so-called faint dwarf, ultra faint galaxies, dwarf galaxies has been observed. So, so gradually, a very faint with low surface brightness galaxies has been observed. So I think that in near future the number will grow somehow. So the discrepancy becomes smaller and smaller. But of course, I don't know to what extent or to what fluctuation scales such consistency holds. So I think basically it is probably the observational bias, but maybe we may need some new physics on very small scales.
Okay.
Anton, you're still mute.
Anton-san,
Oh, sorry.
you can.
Okay. Yeah, thanks, Dr. Hesti. So I should tell you about Dr. Hesti. Dr. Hesti is our chair of undergraduate program in astronomy ITB. Okay, thanks. And then the next question may be coming from Premana-san. Yeah, go ahead.
Thank you. Thank you very much, Professor Inoue, for a very thorough talk. Actually, I have a question regarding on the structure. Well, the first question is probably somewhat related to Dr. Hesti's question, which is the processes that is involved in the galaxy formation. I've actually been wondering about, this missing smaller structure in CDM scenario have been an issue for decades now. And I've been wondering whether there should be a different threshold for different scales, such that in a smaller scale they're more sensitive to dissipative processes, such that you don't get small structure as easily as larger or massive structures. And the other one is your trough. How are they different from void? And I don't know whether it's just your cartoon, or are they elongated, or is it just seen from a certain angle? Because if it's elongated, it's a little bit I don't know, structure formation wise different to manifest. So,
Okay, so
just that for now. Thank you.
I think it is very easy for me to answer the second question, but actually not easy. For trough, such analysis has been already done in the weak ranging people on larger than 1 megapascal scales. I think it is related to voids, but the difference is that we have to consider the integration in the random side. So that means many structures surrounding, with halos also reside in a void. And if we, for instance, some, voids, we can observe many voids in the random side, for instance, right? So if we consider some voice, but it is aligned, something like this. So in that case, we observe negative density perturbation in a particular line of sight path. So that doesn't mean there's a trough structures in the universe, but the point is that for the sight lines, it looks like a trough. So maybe they are in some configuration for the sight lines. For the sight lines, the structures look like troughs because of the existence of many voids with some sort of particular structure. So I think it is probably some sort of artificial structure due to some observational bias using the basically the weak lensing effect, the integration of perturbing effect.
So it's the opposite of finger of God effect. The opposite meaning trough being the underdense and finger of God effect is the positive.
In the case of finger of God, it is related to the velocity dispersion, right? So I think it's a different one. It's just under dense region, the negative gravitational potential perturbation. So on the integrated one, so it is different. But somehow it may look like, because it is not physical.
That's right. It's not physical.
Yeah. In that sense, it is the same. But actual physical structure is, of course, quite different. Yeah. And also, your first question, I didn't understand well. So you are talking about the dissipative.
Yeah. So for smaller structure with very, very faint density contrast, they're more sensitive to dissipative effect. Like a streaming effect or something, which is quite possible in the early universe. So as a result, you only have a strong contrast structures remaining, and therefore you get bigger galaxy. You don't get as many smaller structures. It is not impossible, but it's quite improbable that they remain.
Yeah, I understand your comment. It's actually you're true. For if you considering the sub-halo structure, for instance, in a very large, let's consider a very large galaxy, and many small halos spiral in the process of galaxy formation, but it is affected by the tidal force due to the very large gravitational potential for the primary lensing galaxies. So some sub-halos tidally broken because of the tidal force. Yeah. So no longer small scale structure, something like that. Yeah. But if you consider the line of sight, there are many underdense regions in the whole universe, very large. So in that case, there's no such structures that can affect large. For instance, you can consider the isolated halos or very small halos in the line of sight, at which is no large galaxies cross. So in that case, such isolated halos, I think, remain. So we would be able to measure such a small scale, although it may be susceptible for the dissipative effect, but as a whole, integration, probably there should be some, on very large parts of the universe, there should be some, faint gravitational potential perturbation. Actually, it has been observed. So that I think I hope it will be answered.
Yeah. Thank you very much.
Okay, thanks, Inaya-san, and thanks, Pramana-san. So let's move on to another question. Is there another question? Let me check the chat box. There is one question, but he asked me to read the questions. So what is the advantages of strong gravitational lensing compared to another method for probing dark matter, such as direct detection? What is the advantages?
Advantage.
Okay.
Oh, that is a very good question. Okay. Yeah. There are merit and demerit both. So for the merit, I think we can measure very distant object at the cosmological scales. For instance, redshift of 0.3 or 0.2 or 0.1. I think no other methods can prove the gravitational potential directly. That is the point, I think.
Okay, yeah, thanks. The question has come from Arif Nur Rahman. Thanks for the questions. So maybe we still have time, about 5 minutes. If there is a question from another participants, please. No one. So maybe from my side. So is there any possibility to conduct a collaboration between Kindai and ITB related to your research, especially in strong lensing in the future?
Yes, sure. I'm very welcome because I think this subject is basically interdisciplinary field. For astronomers, it's different because it is physics, and for physics people, it is astronomy. So I think actually very difficult to find people who can collaborate with me. So I'm very happy if one of you are very interested in this subject, and I hope the number of people who are interested in this subject will be increased in the near future.
Yeah, it's true that it's our challenge in strong lensing. We have to increase our human power. Yeah, this is such kind of invitation to young generation to join with us in a strong gravitational lenses topic. Okay, is there any questions? If there is no more questions.
May I one more?
Okay, yeah, please.
Just a quick one. Just a very quick one. Just an opinion. I asked your opinion. How would you compare this to other effort that people use, for example, like integrated Sachs-Wolfe effect, that could be more sensitive to lensing in a certain scale, but missing other obvious feature in the observation? Lensing can be very, very nice if you have nice images, nice signatures in the flux ratios or something, but without those signatures, you miss lensing effect, right? And lensing effect depends so much on our position. And so I was thinking, can you do other things using computer, for example, with integrated Sachs-Wolfe effect?
Okay, so in the case of integrated Sachs effect, I think it is relevant to the more larger scale. I think probably more than 100 megapascal. So we are considering a very small scale physics. It is smaller than 1 megapascal scales. I think of course there should be some degree of integrated Sachs effect also on this scale, some very small scales. But compared to the effect in the cosmological scale, the effect is quite smaller. of course, it may be possible in the future, but I think we should concentrate on more time domain physics, like time delay. Also, such subhalos and random such structures that will affect time delays. Now we can measure the many lensed supernovae, and we can measure the time delay very accurately. So not only the information of the gradient of the potential, but also we can measure directly the integrated potential itself by measuring the time delay, because time delay is proportional to the integrated gravitational potential. So the delta effect of potential itself can be measured, and it's a first derivative, the shift can be measured, and the second derivative, convergence and shear flux ratios, then we can measure. So both three, but you are talking about the time evolution of the gravitational potential, but the time of the photons that pass through the object is very small, very short. So it's very, very challenging. But of course, maybe somehow possible. But still, I don't have any idea for measuring Daxov effect for such integral Daxov effect for such a small size objects.
Yeah, thank you.
Okay, thanks,
Thank you.
Pramana-san. I think that's we don't have time. So yeah, thanks for Inoue-san for joining us today and very fruitful discussions with us. And then I wanna invite all the audience here to thanks Inoue-san for his presentation today. And I want to invite you all to open your video. We will take a picture together. I mean, I want to take a screenshot picture. Okay.
Thank you.
Let me check. Okay. There is 27 participants here. So okay, be ready. I wanna take the first one. 1, 2, 3. Okay, the second one, you can change your face. Okay, let me check. Okay, 1, 2, 3. And then now I invite you all to open your mic and let's thanks to Inoue-san.
Thank you, Inoue.
Thank you, Inoue-san.
Oh, you're welcome. You're welcome. Thank you very much. Thank you very much. I really enjoyed. I really enjoyed. Thank you. Thank you. Bye.
Thank you everyone. Ya, terima